Right, in this video we're going to talk about triple integrals. I'm going to start off with an example. So let's look at the integral from 0 to 1, integral from 0 to 1 minus x. I'm actually going to change some colors in here when I do this. Let's make this one blue. From 0 to 1 minus x. Let's do this guy in green. From 0 to 1 minus x minus y. And we'll make the inside orange. Let's integrate z. And the inside integral was with respect to z. The middle one was with respect to y. And the outside one is with respect to x. Now I've color-coded this in a way that we would actually look at the integral, and the way we're going to look at all triple integrals. We are going to evaluate them and set them up and graph them, and all of this we're going to do by looking at the inside first and then work outwards. So we're going to look at the green first, integrate that, then we'll integrate the blue, then we'll integrate black. Alright, so we're going to integrate the green first. Now notice that I made z different. That is the function that we're integrating, but each different one of the actual integrals themselves has to do with a certain variable. So this first integral that we do, we're going to integrate with respect to z. And what that means is if there was a y or an x in there, it would be constant. So integrating with respect to z, there's a z in there. So that would be a z squared over 2, and we're going to have to evaluate that from 0 to 1 minus x minus y. We can plug that in. 1 minus x minus y. That will all be squared. It's divided by 2. And then we still have these other integrals to worry about. We're going to have to now integrate from 0 to 1 minus x with respect to y. And then after that, we're still going to have to integrate from 0 to 1 with respect to x. Okay. So now integrating with respect to y. So everything else is kept constant. And so that means x is constant. So when we integrate with respect to y, I'm going to do a u substitution here, meaning that we'd have 1 minus x minus y. That would be our u. It is squared, so I'm going to cube it and divide by 3. So that means we're going to divide by 6 now. And because of the derivative of the inside part, I'm also going to divide by a -1. So these are all multiplied together. That -1 is coming from the negative out in front of y when we do our u substitution. So now this needs to now be evaluated from 0 to 1 minus x. So when we plug in 1 minus x, we just integrated with respect to y. So we are going to plug that in just to y, 1 minus x. All of that was cubed over 6. I'm going to put the negative out in front of that. And then minus, we're going to plug in 0 into y, and that leaves us with 1 minus x cubed all over 6, and that 6 is negative. So I'm going to switch the sign of that. Okay, so I plugged in 1 minus x into y here. I plugged in 0 here. These were both divided by -6. I subtracted the lower bound. I subtracted a negative. It made it positive. All right, so I think before I continue to integrate, although I'm going to write the integral sign for this last one. So we're integrating from 0 to 1 now. I'm going to do some simplification first. So I've got this. I'll leave the negative out in front of that one. So I've got 1 minus x and then a -1. So 1 minus 1, those are going to go away. And then I've got a negative x minus a negative x. So negative x plus x, so that goes away. Oh, so I got 0 right there. And then I'm adding 1 minus x cubed over 6. I've got to integrate that with respect to x. So now integrating with respect to x. I'm going to do this same u sub trick. Raise that one to a 4th, divide by 4. 6 times 4 would be 24. And then I'm going to integrate from 0 to 1. So I plug in 1 and get 0. Subtract when I plug in 0. and I get 1/24. And I think in this integration here, look at what I did. There's that negative out in front of there. I forgot about him. So I need to subtract or divide by -27, say. So this would be minus a negative, and so our answer would be 1/24. All right, so that's how to integrate. You integrate the inside first, work your way outwards. Now notice on this integral that I've set up, there's some pretty complicated functions on the inside. And then as you work your way towards the outside is always numbers. And this will always happen. The other thing, I think I have room for it here. If I wanted to graph this, so I'm going to kind of graph this just on the side over here. If you look on the inside function, I've got dz, so z is equal to 1 minus x minus y. So this would be x plus y plus z equals 1. So that's a plane. So the big picture, when I start with the inside, I've got a plane where it crosses each axis at 1. So there's the big picture, and then I want to look outwards and see if those functions affect or kind of chop this plane at all, or if that is where that plane is going to stop. So when you look to the y values here, we've got that y is 1 minus x, and if we graph that, that is the line, y-intercept of 1, ends at 1, and then we also have y equals 0 at the bottom of this graph. And so there's y equals 0, and there's y, that line. And then if we look at the x's are bounded from 0 to 1. X's are bounded from 0 to 1. So in the two-dimensional plane, we're looking at that triangle. And if you look back up to the three-dimensional drawing, it is this exact same triangle, meaning that these outer bounds do not cut that shape at all. It keeps the entire plane. So the plane, or what we essentially are integrating over, is this plane right there. All right, now I do want to specify that we did not find the volume beneath that plane, and the reason that we did not find the volume is that z function right there. All right, let's do another example. All right, so let's, in this next example, calculate the double integral over e of the square root of y squared plus z squared, where e, it's a three-dimensional solid. It's going to be bounded by the paraboloid x equals y squared plus z squared and a plane x equals 9. So some rules here. This is kind of some rules of setting up this triple integral. So for the inside, look for the most complicated function. So that's what I do first. I look for the most complicated function, and I want to try to set up the inside of this integral first. So I'm going to leave some space for these outer ones. And if you notice, really the only function that we have here is this x. So let's use it. So that means that for this inside integral, we've got to put the biggest x on the top and the smallest x on the bottom. And to do this, we really almost need a picture of what's going on. So in these rules, I might even sneak a little rule in here that says draw the picture. Draw a picture, then start thinking about what your most complicated function is. So if we draw the picture of this guy. So this is, oh, I did not leave myself enough room there. Because this is an x equals, it's a paraboloid that comes out towards the x-axis here. There's our x-axis. And it ends right there where x equals 9. X, y, and z. Okay, so this is the paraboloid where x is equal to y squared plus z squared. All right, now looking at this, the biggest value of x, the most x value is that x equals 9. That's the biggest one. The smallest one, as we go back towards the yz plane, we're eventually going to run into that paraboloid. It's the smallest, so y squared plus z squared. And when we did this, we were looking all along the x-axis. So my inner integral is going to have to be with respect to x's. I've got this square root of y squared plus z squared. All right, now for the other two. The other two are y's and z's. And so to simplify that, what I'm going to do is I want to squish this shape onto the yz plane, and then I can figure out the balance from there, because sometimes looking at it three-dimensionally is harder. And for the outer two, we really just have to look at a two-dimensional shape. All right, so maybe I should write down a rule about that. So draw a picture. For the inside, it's the most complicated function. For the outside two, look at a two-dimensional graph. All right, so if I draw this shape, if I squish it onto the yz plane, I get this circle. And to get this circle is what I would see if I squished that onto the xy plane. Now that was where x was equal to 9, and if x is equal to 9, then I have a circle of radius 3. Okay, so now if I wanted to set up this integral, if I wanted to say choose z next, my upper function for z would be the positive square root of 9 minus x squared, and then the bottom bound would be the negative square root of 9 minus x squared. That's the negative root right there. And then the outside integral, so now my y's, those are numbers, so that would go from negative 3 to 3. And I want to kind of write down a rule about that. The outside integral is always numbers. You're never going to have a function in that outside integral. All right, so now I want you to take a look at this. I'm going to get that z out of the way there. So as we take a look at this integral we just created, it's not looking so pretty. We've got this function we need to plug in, we've got a square root we need to integrate, then we're going to plug in other square roots and need to integrate those. So I just realized I made another little error here. I'm sorry, if this is 9 and we were looking at z, and if I solved for z it would be 9 minus y squared. So I need to switch that to a y and that to a y. The reason I noticed that is because my outside integral was y, and if I'd plugged in x's I wouldn't be able to actually get a number out of that. That's kind of what cued me on to that something was wrong there. Okay, so if you look at this graph that we did in the two-dimensional, in this two-dimensional graph of this thing, you notice that we have a circle. And when we have a circle, polar coordinates is way easier to use. So for the outer two, we can switch the z and the y to polar coordinates. We can keep the x as the x, but then we need to switch everything else to polar coordinates. So because we're going to use the yz plane for our polar coordinates, I am going to define the r squared as being a y squared plus z squared in all of this. So when I rewrite this integral, the inside part, y squared plus z squared, was r squared, and we're going to take a square root of that. I'll write out that we have square root of r squared. I'm going to multiply by another r. because when we switch over to dr and d theta, I need an extra r with that dr and that d theta. The inner integral, y squared plus z squared is r squared. 9 will stay as 9. Now for the outer 2, I'm going to look at this two-dimensional graph. The radius is going to go from 0 to 3 on that, and theta goes from 0 to 2 pi. And just notice how much simpler this integral is. So now this one you can solve, start with the x's, and integrate and work your way outwards.